Welcome to Earthly Teachings, where learning is clear and powerful. Today, we are working on Mathematics N6. Let's learn together. In this video, we're going to dive into a very practical skill for solving problems in calculus. That skill is choosing a representative strip. This might sound simple, but the right choice can make the difference between a quick, straightforward solution and a long, complicated one. Our main goal today is to help you develop the intuition to select the best strip, either vertical or horizontal, when you're calculating areas or volumes using integration. By the end of this lesson, you will be able to analyze a bounded area and confidently decide whether to use a vertical strip, integrating with respect to x, or a horizontal strip, integrating with respect to y. We'll look at a few examples to solidify this understanding. Let's begin with our first example. The question asks us to consider an area bounded by several lines and a curve. The area is bounded by the curve y equals e to the x, the line x equals 2, the x-axis, and the y-axis. The first step in any problem like this is to visualize the area. Let's sketch it on a coordinate plane. First, we draw our coordinate axes. Then we plot the curve y equals e to the x. This curve starts at y equals 1 when x is 0, since e to the power of 0 is 1. It then grows exponentially. Next, we draw the vertical line x equals 2. This line cuts our curve at the point where x is 2. The y-coordinate here would be e to the power of 2, which is about 7.39. Our bounding lines are also the x-axis, where y equals 0, and the y-axis, where x equals 0. The area bounded by all four is this region you see shaded in gray. Our task is to find a strip that makes finding this area as straightforward as possible. Let's see what happens if we choose a horizontal strip. Now, let's explore our first option, using a horizontal strip. Remember, a horizontal strip means we will integrate with respect to y. If we choose a horizontal strip, as shown in this first figure, we immediately run into a problem. The function that forms the right-hand boundary of our strip changes depending on where the strip is located. For a strip in the lower part of the region, from the x-axis up to y equals 1, the right-hand boundary is the vertical line x equals 2. So here, a strip from the y-axis to x equals 2 has a length of 2. The area of this lower part would be the integral of 2 with respect to y. But what happens when our strip moves above y equals 1? Now, the right-hand boundary is no longer the line x equals 2. It's the curve y equals e to the x. This means the length of our strip is now the x value on the curve, not a fixed value. Since the function that defines the strip's length changes at y equals 1, we must split our integration into two separate parts. We would need two different definite integrals to find the total area. This is a common situation to look for. If your strip's boundary changes, you likely need multiple integrals. There's another issue with the horizontal strip. To integrate with respect to y, our functions must be written in terms of y. That is, we need x equals f of y. The equation of our curve is y equals e to the x. To solve for x, we would have to take the natural logarithm of both sides, giving us x equals the natural log of y. While this is certainly possible to integrate, it adds a layer of complexity we might want to avoid. The goal is to make the problem as easy as possible. So, in summary, using horizontal strips for this problem would force us to do two calculations and would require converting our function to a natural logarithm. This is not the most efficient choice. Now, let's look at the alternative. What if we use a vertical strip instead? A vertical strip means we will integrate with respect to x. As shown in this second figure, the situation is much simpler with a vertical strip. For the entire area, the top boundary of our strip is always the same curve, y equals e to the x. And the bottom boundary of our strip is always the x-axis, or y equals 0. This is the key difference. Since the function that forms the top boundary of our strip never changes across the entire region, we only need to perform one single integration. The area of this strip is its height, y equals e to the x times its width, which we call dx. We can express the height as top function minus bottom function, so it's e to the x minus 0. The integral for the total area would then be the integral from x equals 0 to x equals 2 of e to the x dx. This is a very straightforward calculation. So, to recap this example, the vertical strip was the clear winner. It required only one calculation and didn't force us to rewrite our function in a more complex form. We've seen how to analyze a bounded area and choose the correct integration strip. Let's move on to a second example, as these patterns for choosing a strip are incredibly useful. This time, we're looking at an area bounded by two lines and the x-axis. The area is bounded by the line y equals 2x, the line y equals 2 minus 1/2 x, and the x-axis. As always, our first step is to visualize this region. Let's draw the lines. The first line, y equals 2x, passes through the origin. The second line, y equals 2 minus 1/2 x, crosses the y-axis at 2 and the x-axis at 4. The problem also gives us the point where these two lines intersect. They intersect at the point 4, 5, 8, 5. You can check this by setting the two equations equal to each other. 2x equals 2 minus 1/2 x. Solving for x, we get 2.5x equals 2, or 5 and 2x equals 2, so x equals 4, 5. Plugging this back into y equals 2x gives y equals 8, 5. So the intersection point is indeed 4, 5, 8, 5. Now we can identify the shaded area. It's a triangle with vertices at the origin, so the intersection point A, and the point B where the line y equals 2 minus 1/2 x crosses the x-axis. Let's test our strategy by choosing a vertical strip first. We're now considering the area bounded by y equals 2x, y equals 2 minus 1/2 x, and the x-axis. Let's see what happens with a vertical strip. Figure 5.21 shows the area with a vertical strip of width dk. We can draw the strip anywhere in the region. Notice what happens as we move the vertical strip across the shaded area. In the left part of the triangle, from the origin to the intersection point at x equals 4, 5, the top boundary of our strip is the line y equals 2x. The bottom is the x-axis. So for this part, the area of the strip is 2x times dx. This defines the first part of our integral. But when the strip moves past x equals 4, 5 into the right part of the triangle, the top boundary suddenly changes. Now it's the line y equals 2 minus 1/2 x. For this second part, the area of the strip is 2 minus 1/2 x times dx. The boundary has changed. Just like our last example, because the top function changes at x equals 4, 5, we would need to split our total area into two separate integrals, one from 0 to 4, 5, and another from 4, 5 to 4. Although perfectly doable, this strategy requires two separate calculations. It's not the most efficient path. This tells us to look for a better option. When you see a vertical strip cross a point where the top function changes, you should consider using horizontal strips instead. We just saw that a vertical strip for this area requires two separate integrals. Now let's try using a horizontal strip. Remember, a horizontal strip means we will integrate with respect to y. Figure 5.22 shows the same triangular area, but with a horizontal strip. Let's see how this one behaves. Consider a horizontal strip of height die somewhere in the shaded region. The left boundary of the strip is on the line y equals 2x. The right boundary is on the line y equals 2 minus 1/2 x. Notice that for any value of y within the triangle, the left boundary is always the first line, and the right boundary is always the second line. The functions do not change. This is great, but to find the length of the strip, we need to find the x values of its ends. To do that, we must rewrite our equations to solve for x in terms of y. From y equals 2x, we get x equals y over 2. This is the x-coordinate of the left end. From y equals 2 minus 1/2 x, we get 1/2 x equals 2 minus y, and multiplying by 2, we find x equals 4 minus 2y. This is the x-coordinate of the right end. Now the length of the horizontal strip is the x-coordinate of the right boundary minus the x-coordinate of the left boundary. This gives us 4 minus 2y minus y over 2, which simplifies to 4 minus 2.5. This single expression for the length of the strip is valid for the entire triangle, so we can use a single integral. The area is the integral of 4 minus 2.5y dy. The integration is with respect to y. What are our limits of integration? We need the lowest and highest y values in our region. The lowest y value is 0 on the x-axis. The highest is the y value of the intersection point A, which is 8, 5. So our limits are from 0 to 8, 5. The integral we need to solve is the integral from 0 to 8, 5 of 4 minus 2.5 dy. This is a simple polynomial to integrate. Compared to two separate integrals with vertical strips, this is clearly the easier method. So, we've now seen two key strategies. First, if your strip's boundary function changes, split the integral. Second, and more importantly, always ask yourself, would switching the strip orientation avoid a change in boundaries? If so, it will likely save you a lot of work. Our final example demonstrates another important rule to remember when choosing a strip. We're looking at the area under a sine wave. The area is bounded by the curve y equals sine of x, the line x equals pi over 2, and the x-axis. Let's sketch the area. The curve y equals sine of x completes one wave between x equals 0 and x equals pi. The line x equals pi over 2 is the vertical line at the peak of this wave. The bounded area is this region you see shaded. Its vertices are the origin, the point pi over 2, 1 on the sine curve, and the point pi over 2 as 0 on the x-axis. Let's first think about using a horizontal strip, and you'll see why it's usually not the best choice when dealing with trigonometric functions. To integrate with a horizontal strip, we'd need x equals f of y. This means we'd have to solve y equals sine x for x. Solving e equals sine x for x gives us x equals the inverse sine, or arcsine, of y. Integration is the reverse of differentiation. Differentiating arcsine y gives 1 over the square root of 1 minus y squared. Integrating that result gives us back arcsine y. This is a special function, and its integral can be much more involved than other types of functions. So, our integration would look like this, the integral of arcsine midi. While it's possible, it's generally more complex than necessary. For this reason, we have a memory tip. As a rule of thumb, when you have a function that represents a trigonometric curve, you should always try to use a vertical strip. Let's see how much simpler it makes this problem. We just saw that a horizontal strip for our sine curve led to a complex inverse trigonometric function. Now let's try a vertical strip. Figure 5.23's left graph shows our area with a vertical strip of width dx. Let's analyze it. For any point in our shaded area, the bottom boundary of our vertical strip is the x-axis, which is y equals 0. The top boundary is the curve y equals sine of x. Notice that the top function never changes. It's always y equals sin mu. This is the first positive sign that a vertical strip is a good choice. We don't need to split the integral. The height of our strip is the top function minus the bottom function, which is sine of x minus 0, or simply sine of x. The area of this strip is its height, sine x, times its width, dx. Now, what about our limits of integration? Since we're integrating with respect to x, we need the minimum and maximum x values in our region. The region starts at x equals 0 and ends at the line x equals pi over 2. So our limits are from 0 to pi over 2. The integral for the area is the integral from 0 to pi over 2 of sine x dx. The integral of sine x is negative cosine x. Evaluating this from 0 to pi over 2 gives negative cosine of pi over 2 minus negative cosine of 0. Cosine of pi over 2 is 0, and cosine of 0 is 1. So we get 0 minus negative 1, which equals 1. The area is exactly 1. Compare that to the arcsine integral we imagined earlier. A vertical strip led us to a simple calculation and a clean answer. This is a perfect example of why choosing the correct strip is so important. Let's quickly recap the key guidelines we've established today for choosing a representative strip. First and most important, choose the strip orientation, vertical or horizontal, that requires the fewest integrals. This usually happens when the top and bottom or left and right boundary functions of the strip never change across the entire region. Second, choose the strip that leads to the simplest integration. Sometimes you have to choose between, say, integrating a natural log and integrating a polynomial. Go with the polynomial. A key trap to avoid is converting trigonometric functions into inverse trigonometric functions. Remember our memory tip. Stick to vertical strips for trig curves. Finally, when you set up your integral, always ensure your equations are in the correct form. If you're using a vertical strip, integrating with respect to x, your functions must be y equals f of x. If you're using a horizontal strip, integrating with respect to y, your functions must be x equals g of y. A common mistake is to mix these up. By following these guidelines, you'll be well equipped to tackle any area or volume problem you encounter in Mathematics N6. Today, our objective was to learn how to choose the correct integration strip. We've achieved that by analyzing the boundaries of a region and prioritizing simplicity. This skill will make your integration problems much more manageable. Thank you for watching this tutorial on earthly teachings. I hope you found it clear and helpful. If you did, please give the video a like. Don't forget to subscribe to the channel for more powerful lessons in Mathematics N6 and beyond. Keep practicing these concepts, and you'll find them becoming second nature. See you in the next video.